Alright guys, so welcome back to our class again. In this experiment, we want to determine the resistance per unit length of a wire. And to achieve that, we have a potentiometer here, a key here, and a resistor of about 5 ohm, as you can see here. Then a zero center galvanometer, which we have, and then a bare wire of about 100 centimeters length, and a source of EMF, which you have here is about 3 volts, and of course a connecting wire, and of course a crocodile clip, and then a jockey finally. Now we are going to set up this experiment as it is, as you're seeing it on the screen now, and then we would proceed to find the resistance per unit length of this wire. Okay, we are through with the setup, and this is a run through of what we did. You can check the diagram you're seeing now. From the down part of the potentiometer, we have here the cell connected in series with the key, and then connected to the other end. Now from this right end of the potentiometer, we have the 5 ohm resistor connected, and then it's connected in series with the galvanometer, and then the other end of the galvanometer is connected to the jockey, which we are going to use in tapping the potentiometer wire. However, from this other end, we now looped in to form we've looped in the crocodile clip from the other end. According to the drawing, you can see it there, which we will use to hold the resistance wire, which is connected at the other end. You can see that the circuit is now complete. Now while you're conducting this experiment, don't allow this resistance wire to touch any metallic object. If not, of course, you expect that current will flow, and then it will in a way affect your reading, so be mindful. All right, so having made up this circuit, we are going to proceed. Now the essence of the meter is to measure the length. I've already done that. So the length of the wire is from here to here. It's about 20 cm. We're going to repeat that during the course of the experiment for 40, 60, 80, and 100. So I'm starting with 20 at the moment. So I've measured that. So I'm going to find out the balance length. Once I tap, I'm first of all going to test for continuity now. So once I confirm that my setup is working appropriately, I'm going to find the balance length. At the balance length, the galvanometer reading is meant to be reading 0, even though current is flowing through it. So once I deduce my balance length, for example, if my balance length is at 40 or at 50, I will record the distance from 0 to this point as my y1, and then from here to here as my y2. I will record that because in the question they asked us to evaluate y1 over y2, and then the length of the wire is also recorded. We are going to have that, and then the value of the resistor, we use 5 ohms, which is R, is also going to be needed in subsequent calculations. So let us take our readings and proceed from there. So now that we have measured for 20 cm, let us see whether, let's test for continuity. 50 here, you can see there's a deflection, so it's continuous. You can see current is flowing through. Here is 40. So I'm looking at for the balance length. Here is 30. It's still away, or it's close. 29. It's pretty much close. 28. It's not there yet. 27. Okay, 27 is there. Let's see 26 whether it will cross. 26. 26, 25, 25 is exceeding it gradually. 24, you can see 24, right? So this is 23. So the farther I go, you can see the more it's being deflected. From here is 0.23. So let's go back to 25. Here is 0.25. 25 is not close. Let's check 26. Here is 26. 26 at eye level is not exactly there. Let's check 27. So here is 27. 27 is perfectly at 0, so you can see. So our balance length is 27. So it means my Y1 is 27 and my Y2 is 100 minus 27, which will give you 73. So this is what we have for this first reading of 20 cm. Now I'm going to record this and then go change the length of the wire to 40. We'll also find the balance length. All right, as we proceed to the next step, I've measured this wire here to be about 40 cm in length, and I'm going to repeat the same procedure of finding out the balance point on the galvanometer. So let us see what we can get from here. Let me also start from the center mark. Here is 50, is to the right. Let me go to 40. 40 is already to the left, so it means it's beyond 40. So let me say 41 gradually now. 41 is just close. Let's do 42. Here is 42. 42 is on it. Let's see 43. Let's see what 43 will give us. 43 is at eye level, you can see it's just a little bit beyond it. Let's see 44 so that we can confirm. So here is 44. You can see that 44 is also beyond. Let's see 45. Okay, so you can see it is going beyond. So let's take it to 43 again and see what happens. So here is 43. Here's 40.43 here. Is exactly at G. So it means that my Y1 is 43 and my Y2 is 100 minus 43. I will change this length also to 60 and see what we will get. Okay, so I have also adjusted and measured out 60 cm from this wire here. And the same thing we've done before is what I'm going to do quickly. I'm going to find out the balance length. Let me start from 60. From 60, I have here a full deflection to the right. All right, let me come to 57. 57 is closer. Let me come to 56. 56 is also coming closer. Let me come to 55. 55 is close but not there. Let me come to 54. 54 is very close but not exactly there. Let me see 53.5. 53.5. Here is 53.5, and then we have 53.5. Oh, okay, let me use 53. So 53 is the one giving me the accurate value. Here is 53 here, and this is the value at eye level. Here is 0. 53 is the one that is giving me 0 deflection. So if I move this beyond this, you can see that it has gone below. If I go back forward, it will also show you that current is flowing. So 53 is the one. Don't just assume. Most times the reason why I had to, even after confirming the value, to tap another point is to confirm that current is still flowing in the circuit, so that you don't assume, because if current is not flowing like now, it will be at 0. So you have to be sure that current is flowing through the circuit, so that the point you have confirmed would be your balance point. So this is what we've gotten. So the Y1 for this particular set of experiment is 53, and the Y2 will be 100 minus 53. I'm going to record that, and then I'll change this to 80 cm, and we'll repeat the same procedure again. All right, so guys, I've measured here the length of the wire to be about 80 cm in length. So let me find out what the balance point will be now. So let me start from 70. Here is 0.70. So I'll tap 0.70 here, and you'll see there is a deflection to the right. Let me check 68. Let me tap point 68 here. You will see also there's a deflection to the right. So I'll continue until I get here is 0.66, here is 0.64. You're seeing that we're approaching the zero mark. Here is 0.62. Okay, are you seeing something? So we are not there yet, but we are very close. So it means that it has to be between 0.61 and 62. So let's go to 61 and see whether it will deflect to the left. So let's see, this is 61. 61 is not exactly at 0, just a little bit below. So it means that it has to be between 61 and 62. So let me use 61.5. So this is 61.5. And then let's see what we have. 61.5 is exactly at 0 mark. So it means that my Y1 will be 61.5, while my Y2 will be 100 minus 61.5. So I have just one more to go, which is the 100 cm mark, and then we'll tabulate our reading. All right, finally, I have here the length of the wire to be at 100 centimeters, and my circuit is still intact as we have connected it all along during the course of the experiment. Now, let us find out what the balance length will be. I have here, let me start, where do I start from now? Let me start from 80. So let me tap 0.80 here. So let's see, you can see there's a deflection to the right. Let me tap 0.75. Yes, 0.75. Also check, you will see that the deflection is coming close to 0. Let me tap 0.73. Yes, 73. Let's see, it is pretty much close to G, as you can see here. Then let me tap 71. 71 is almost there, but not there. So it means that we are just about close to it. So let me tap 70. Here's 0.70 here, and let's see what happens. So at this point, we still have it above. You can see. So let's say 69. 69 is not exactly there yet, it's just close. Let's say 68. Okay. So 68 is there. Let's say 67. So 67, you can see it's just to the left, just to the left. 67. All right, I'm seeing semblance with 68 and 67. Okay, let's see lower values. Lower values like 65. Okay, it's down now. 66 is not there yet. 67 now, again there. 68, I'm seeing that 67 and 68 are there. We really need to differentiate which one is which. 68, okay, 68 is actually above, so it means 67 should be the most acceptable. Yeah, so here is the 67 mark, and that is the one that gives us 0 deflection. So we are going to record this as our final value, 67 centimeters. Recall that this is our Y1, while the other part will be the Y2, that is 100 minus 67. So this is the reading aspect. I'm also going to tabulate the reading and then plot a graph, and then we'll answer the questions that follow. So stay tuned. Okay guys, here is the result of our experiment. You can see that this table is well compiled with the length of the wire all written down in appropriate decimal places. Remember that anytime you are representing your data in a table, you must have to take note of the reading accuracy of the measuring instrument you use to measure. If we use the meter rule, and to be safe, you can see we put 0.00 just to be safe. Anything more is acceptable, but not lower than 0.1 cm. Now for Y1, which we measured yesterday, is also compiled. Y2 is also compiled. Then they say we should evaluate P, which is Y1 over Y2, and then Q, which is equal to length of wire divided by the resistance, which was given as a fixed value for 5 ohms. So by the time we compiled everything here, we have a table neatly arranged. Now with this table now, we are asked to plot a graph with P on the vertical axis and Q on the horizontal axis. This is what that graph is all about. You can see that the axis of this graph is distinguished with P on the vertical axis and then Q on the horizontal axis. A graph of P against Q also written. The tracing is there for us, and then the slope triangle is also neatly represented, a bold right angle triangle. Now, interpreting this graph further, we'll use it to deduce the slope, and the slope would be simply the change or the ratio of the change in P to the change in Q. And our calculation gave us a value of 0.1083 ohms. And that was what led to the second question, because they asked us that we should state what is the significance of the slope. So the significance of the slope, of course, from the unit tells you that it represents electrical resistance. Of course, whenever you conduct an experiment, there must be a precaution that you must have stated or you must have taken during the conduction of the experiment. Now, in this experiment, we ensure tight connection. For every electricity experiment, this is actually an expectation for you. And then we avoided parallax error in reading the meter bridge, the meter rule we use in measuring the wire, and of course the galvanometer. We also removed the terminals of the key when we are not taking any reading at all in order to preserve the cell. And then we avoided scraping the jockey on the potentiometer wire. That is, you don't scrape the jockey on the potentiometer wire. That is not acceptable during an electricity experiment. And then finally here, we avoided zero error in reading the galvanometer as well. So any two amongst all of these can suffice. Just feel free to explore any one of them. Now, going further, they asked us to a question. They say two standard resistors A and B have resistances RA and RB respectively, such that RA is greater than RB. Say using the same axis of a graph, we should show the relationship between the voltage and current for both A and B. Now, you know that from Ohm's law, we know that V is equal to IR. And if we make R subject formula, would get that R is equal to V over I. In other words, if we now plot a graph of V against I, we can find the slope or the slope line to be equivalent to the resistance. Now in this particular question, they told us that RA is greater than RB. So if we were to plot the same, represent this using the same axis of a graph, it means that the RA will be higher or greater than RB in the graph as well in terms of its representation. So here you can see in this answer that we represented both of them in a graphical form. Since we don't have any values, so we can't assign values. Assuming in the question there are values, then we can actually trace it properly and show it based on the values which are given to us, which is given to us. But in this case, we just have to represent diagrammatically. So we have A above B to indicate that the resistance of A is greater than the resistance of B. So this is just a simple way to represent this answer, this question. And after that, they now ask us that from the graph that we should determine the value of V0, leaving our answer as a fraction based on the diagram that is given to us. Now, if you take a look at this diagram, you will notice that this is a circuit. It's a potential divider circuit. And in this potential divider circuit, the voltage in, or the V in, or the EMF of the cell is equal to 40 volts. So the initial voltage, which is the voltage in, as we call it here, is 40 volts. And then it's connected across two resistors. but we want to find the voltage that is coming out, the V naught, and that voltage is across the 10 ohm resistor. So if we are to solve this, remember, make reference to our previous videos on potential dividers. So we started off, in order for the people that are not grounded in this to understand the background, we started by explaining what a potential divider is. We said it's any circuit that is arranged or designed to reduce the voltage by a certain fraction. So the reason why we do the connection is just in such a way that we can be able to reduce the voltage by a fraction. So in order to solve these problems, you have to choose a resistor value that will give you that certain part of the value of that certain part of the circuit that you want to reduce the voltage specifically. So if you check the diagram that we have, you will see that the V in, which is the initial voltage, is 40 volts. The V out, which is the final voltage, is what we are looking out for. The initial resistance, R1, is given as 5 ohms, and the R2 is given as 10 ohms. Now, this formula, check our video on potential dividers, you will see how we explained it there, is V out is equal to R2 over R1 plus R2. That's the ratio of R2 to the sum of R1 and R2 times the voltage in, that is the initial voltage. By the time we substituted everything, we got 80 over 3 volts, because the answer should be in fraction as they requested. But if you want to leave your answer in a decimal point, but under normal circumstance, then you can have it as 26.67 volts. So this is the accurate answer or solution to this particular question. Still going forward in that same diagram, they say we should determine the ratio of the output voltage to the input voltage. So in this case, the ratio of the output voltage, from that same formula we stated earlier, just find the ratio of the output voltage to the input voltage. That will give us the R2 over that's the ratio of the R2 over the sum of R1 and R2. So by the time we also keenly substitute everything, we are going to get 0.667, right? So this is actually the ratio that we have, or if it is in fraction, it's going to be 2:3, as the case may be. So this is just what they asked us in that particular question, and we've been able to break down everything as it was in this particular examination, and we believe that it has been really of help to you. You can make reference to our related videos across these particular terminologies so that you can get more support. We appreciate your staying close. We appreciate you. God bless you. Thank you very much, and remain blessed.